In combinatorics, Ramsey's theorem states that one will find monochromatic cliques in any edge labeling of a sufficiently large complete graph. To demonstrate the theorem for two colors, let R and S be any two positive integers. Ramsey's theorem states that there exists a least positive integer R for which every blue-red edge coloring of the complete graph on R vertices contains a blue clique on R vertices or a red clique on S vertices, signifies an integer that depends on both R and S. Ramsey's theorem is a foundational result in combinatorics. The first version of this result was proved by F. P. Ramsey. This initiated the combinatorial theory now called Ramsey theory, that seeks regularity amid disorder. General conditions for the existence of substructures with regular properties. In this application it is a question of the existence of monochromatic subsets, that is, subsets of connected edges of just one color. An extension of this theorem applies to any finite number of colors, rather than just two. More precisely, the theorem states that for any given number of colors, C, and any given integers n1, nc, there is a number R, such that if the edges of a complete graph of order R are colored with C different colors, then for some I between 1 and C, it must contain a complete subgraph of order Ni whose edges are all color I. The special case above has C equals 2. Example, R equals 6. In the two-color case, an arbitrary simple graph G equals can be identified with the complete graph on the vertex set V whose edges are colored with two colors. This permits talking about Ramsey's theorem using connected and non-connected terminology instead of colors. But this language does not generalize to a greater number of colors. In the following example, the formula R provides a solution to the question which asks for the minimum number of vertices a graph must contain in order to ensure that either at least 3 vertices in the graph are mutually connected, or at least 3 vertices in the graph are mutually unconnected. The remainder of this article will use the more common color terminology and refer to monochromatic cliques. Note that owing to the symmetrical nature of the problem space, R is equal to R. Suppose the edges of a complete graph on 6 vertices are colored red and blue. Pick a vertex. There are 5 edges incident to V and so at least 3 of them must be the same color. Without loss of generality we can assume at least 3 of these edges, connecting the vertex V to vertices R, S and T, are blue. If any of the edges are also blue then we have an entirely blue triangle. If not, then those 3 edges are all red and we have an entirely red triangle. Since this argument works for any coloring, any K6 contains a monochromatic K3, and therefore R6. The popular version of this is called the theorem on friends and strangers. An alternative proof works by double counting. It goes as follows. Count the number of ordered triples of vertices x, y, z, such that the edge is red and the edge is blue. Firstly, any given vertex will be the middle of either 0 times 5 equals 0, 1 times 4 equals 4, or 2 times 3 equals 6 such triples. Therefore, there are at most 6 times 6 equals 36 such triples. Secondly, for any non-monochromatic triangle, there exist precisely 2 such triples. Therefore, there are at most 18 non-monochromatic triangles. Therefore, at least 2 of the 20 triangles in the K6 are monochromatic. Conversely, it is possible to two-color a K5 without creating any monochromatic K3, showing that R greater than 5. The unique coloring is shown to the right. Thus R equals 6. The task of proving that R6 was one of the problems of William Lowell Putnam mathematical competition in 1953. Proof of the theorem. Two-color case. First we prove the theorem for the two-color case, by induction on R plus S. It is clear from the definition that for all n, R equals 1. This starts the induction. We prove that R exists by finding an explicit bound for it. By the inductive hypothesis R and R exist. Lemma 1. R plus R. Proof. Consider a complete graph on R plus R vertices whose edges are colored with two colors. Pick a vertex V from the graph, and partition the remaining vertices into two sets M and N, such that for every vertex W is in M if is blue, and W is in N if is red. Because the graph has R plus R equals M plus N plus 1 vertices, it follows that either M, R or N, R. In the former case, if M has a red case, then so does the original graph and we are finished. Otherwise M has a blue KR-1 and so M, V, has blue KR by definition of M. The latter case is analogous. Thus the claim is true and we have completed the proof for two colors. Note: in the two-color case, if R and R are both even, the induction inequality can be strengthened to R plus R minus 1. General case. We now prove the result for the general case of C colors. The proof is again by induction, this time on the number of colors C. We have the result for C equals 1 and for C equals 2. Now let C greater than 2. Lemma 2. Our R. Proof. Consider a graph on T vertices and color its edges with C colors. Now, go colorblind, and pretend that C-1 and C are the same color. Thus the graph is now colored. By the inductive hypothesis, it contains either a KNI monochromatically colored with color I for some 1 IC-2 or a KR colored in the fluid color. In the former case we are finished. In the latter case, we recover our sight again and see from the definition of R we must have either a monochrome KNC-1 or AC monochrome KNC. In either case the proof is complete. The right-hand side of the inequality in lemma 2 only contains Ramsey numbers for C-1 colors and 2 colors, and therefore exists and is a finite number T, by the inductive hypothesis. Thus, proving the claim will prove the theorem. Ramsey numbers. The numbers R in Ramsey's theorem are known as Ramsey numbers. The Ramsey number, R, gives the solution to the party problem, which asks the minimum number of guests, R, that must be invited so that at least M will know each other or at least N will not know each other. In the language of graph theory, the Ramsey number is the minimum number of vertices, V equals R, such that all undirected simple graphs of order V contain a clique of order M, or an independent set of order N. Ramsey's theorem states that such a number exists for all M and N. By symmetry, it is true that R equals R. An upper bound for R can be extracted from the proof of the theorem, and other arguments give lower bounds. However, there is a vast gap between the tightest lower bounds and the tightest upper bounds. There are also very few numbers R and S for which we know the exact value of R. Computing a lower bound L for R usually requires exhibiting a blue-red coloring of the graph KL-1 with no blue KR subgraph and no red K's subgraph. Upper bounds are often considerably more difficult to establish. One either has to check all possible colorings to confirm the absence of a counterexample, or to present a mathematical argument for its absence. A sophisticated computer program does not need to look at all colorings individually in order to eliminate all of them. Nevertheless, it is a very difficult computational task that existing software can only manage on small sizes. Each complete graph not has 1/2 edges, so there would be a total of C2 graphs to search through if brute force is used. Therefore, the complexity for searching all possible graphs is O for C colorings and an upper bound of N nodes. As described above, R equals 6. It is easy to prove that R equals 4, and, more generally, that R equals S for all S. A graph on S-1 nodes with all edges colored red serves as a counterexample and proves that RS among colorings of a graph on S nodes. The coloring with all edges colored red contains a S-node red subgraph, and all other colorings contain a 2-node blue subgraph. Using induction inequalities, it can be concluded that R plus R minus 1 equals 9, and therefore R plus R 18. There are only 2 graphs among 6.4 times 1022 different 2 colorings of 16-node graphs, and only 1 graph among 2.46 times 1026 colorings. It follows that R equals 18. The fact that R equals 25 was first established by Brendan Mackay and Stanislaw Radziszewski in 1995. The exact value of R is unknown, although it is known to lie between 43 and 49. In 1997, Mackay, Radziszewski and XOO employed computer-assisted graph generation methods to conjecture that R equals 43. They were able to construct exactly 656 graphs, arriving at the same set of graphs through different routes. None of the 656 graphs can be extended to a graph. For R with S greater than 5, only weak bounds are available. Lower bounds for R and R have not been improved since 1965 and 1972, respectively. R with S10 are shown in the table below. Where the exact value is unknown, the table lists the best known bounds. R with S less than 3 are given by R equals 1 and R equals S for all values of S. Note that since R equals R, there is a trivial symmetry across the diagonal. Asymptotics. The inequality R plus R may be applied inductively to prove that in particular, this result, due to Ordos and Chequeras, implies that when R equals S, an exponential lower bound was given by Ordos in 1947 and was instrumental in his introduction of the probabilistic method. There is obviously a huge gap between these two bounds. For example, for S equals 10, this gives 101 R 48,620. Nevertheless, exponential growth factors of either bound have not been improved to date and still stand at 4 and square root 2 respectively. There is no known explicit construction producing an exponential lower bound. The best known lower and upper bounds for diagonal Ramsey numbers currently stand at due to Spencer and Conlin respectively. For the off-diagonal Ramsey numbers R, it is known that they are of order. This may be stated equivalently as saying that the smallest possible independence number in an n-vertex triangle-free graph is the upper bound for R is given by Ajtai, Kamlose, and Simaredi, the lower bound by Kim. More generally, for off-diagonal Ramsey numbers, R, with S fixed and T growing, the best known bounds are due to Bowman and Kivash and Ajtai, Kamlose and Simaredi respectively. A multicolor example. R equals 17. A multicolor Ramsey number is a Ramsey number using 3 or more colors. There is only one non-trivial multicolor Ramsey number for which the exact value is known, namely R equals 17. Suppose that you have an edge coloring of a complete graph using 3 colors, red, yellow and green. Suppose further that the edge coloring has no monochromatic triangles. Select a vertex V. Consider the set of vertices that have a green edge to the vertex V. This is called the green neighborhood of V. The green neighborhood of V cannot contain any green edges, since otherwise there would be a green triangle consisting of the 2 endpoints of that green edge and the vertex V. Thus, the induced edge coloring on the green neighborhood of V has edges colored with only 2 colors, namely yellow and red. Since R equals 6, the green neighborhood of V can contain at most 5 vertices. Similarly, the red and yellow neighborhoods of V can contain at most 5 vertices each. Since every vertex, except for V itself, is in one of the green, red or yellow neighborhoods of V, the entire complete graph can have at most 1 plus 5 plus 5 plus 5 equals 16 vertices. Thus, we have R17. To see that R17, it suffices to draw an edge coloring on the complete graph on 16 vertices with 3 colors that avoids monochromatic triangles. It turns out that there are exactly 2 such colorings on K16, the so-called untwisted and twisted colorings. Both colorings are shown in the figure to the right, with the untwisted coloring on the top, and the twisted coloring on the bottom. In both colorings in the figure, note that the vertices are labeled, and that the vertices V11 through V15 are drawn twice, on both the left and the right, in order to simplify the drawings. Thus, R equals 17. If you select any color of either the untwisted or twisted coloring on K16, and consider the graph whose edges are precisely those edges that have the specified color, you will get the clique graph. It is known that there are exactly two edge colorings with three colors on K15 that avoid monochromatic triangles, which can be constructed by deleting any vertex from the untwisted and twisted colorings on K16, respectively. It is also known that there are exactly 115 edge colorings with three colors on K14 that avoid monochromatic triangles, provided that we consider edge colorings that differ by a permutation of the colors as being the same. Extensions of the theorem. The theorem can also be extended to hypergraphs. An M-hypergraph is a graph whose edges are sets of M vertices. In a normal graph, an edge is a set of two vertices. The full statement of Ramsey's theorem for hypergraphs is that for any integers m and c, and any integers n1, nc, there is an integer r such that if the hyperedges of a complete M-hypergraph of order r are colored with c different colors, then for some I between 1 and c, the hypergraph must contain a complete sub-M-hypergraph of order n whose hyperedges are all color I. This theorem is usually proved by induction on M, the hyperness of the graph. The base case for the proof is M equals 2, which is exactly the theorem above. Infinite Ramsey theorem. A further result, also commonly called Ramsey's theorem, applies to infinite graphs. In a context where finite graphs are also being discussed, it is often called the infinite Ramsey theorem, as intuition provided by the pictorial representation of a graph is diminished when moving from finite to infinite graphs. Theorems in this area are usually phrased in set-theoretic terminology. Theorem. Let X be some countably infinite set and color the elements of X in C different colors. Then there exists some infinite subset M of X such that the size n subsets of M all have the same color. Proof. The proof is by induction on n, the size of the subsets. For n equals 1, the statement is equivalent to saying that if you split an infinite set into a finite number of sets, then one of them is infinite. This is evident. Assuming the theorem is true for n r, we prove it for n equals r plus 1. Given AC coloring of the elements subsets of X, let A0 be an element of X and let Y equals X, A0. We then induce AC coloring of the R element subsets of Y, by just adding A0 to each R element subset of X. By the induction hypothesis, there exists an infinite subset Y1 of Y such that every R element subset of Y1 is colored the same color in the induced coloring. Thus there is an element A0 and an infinite subset Y1 such that all the element subsets of X consisting of A0 and R elements of Y1 have the same color. By the same argument, there is an element A1 in Y1 and an infinite subset Y2 of Y1 with the same properties. Inductively, we obtain a sequence A0, A1, A2, such that the color of each element subset I, with I less than I depends only on the value of I. Further, there are infinitely many values of I such that this color will be the same. Take these I's to get the desired monochromatic set. Infinite version implies the finite. It is possible to deduce the finite Ramsey theorem from the infinite version by a proof by contradiction. Suppose the finite Ramsey theorem is false. Then there exist integers c, n, t such that for every integer k, there exists AC coloring of without a monochromatic set of size t. Let ck denote the C colorings of without a monochromatic set of size t. For any k, the restriction of a coloring in ck plus 1 to is a coloring in ck. Defined to be the colorings in ck which are restrictions of colorings in ck plus 1. Since ck plus 1 is not empty, neither is. Similarly, the restriction of any coloring in is in, allowing one to define as the set of all such restrictions, a non-empty set. Continuing so, define for all integers m, now, for any integer k, and each set is non-empty. Furthermore, ck is finite as. It follows that the intersection of all of these sets is non-empty, and then every coloring in dk is the restriction of a coloring in dk plus 1. Therefore, by unrestricting a coloring in dk to a coloring in dk plus 1, and continuing doing so, one constructs a coloring of without any monochromatic set of size t. This contradicts the infinite Ramsey theorem. If a suitable topological viewpoint is taken, this argument becomes a standard compactness argument showing that the infinite version of the theorem implies the finite version. Directed graph Ramsey numbers. It is also possible to define Ramsey numbers for directed graphs. Let R be the smallest number Q such that any complete graph with singly directed arcs and with Q nodes contains an acyclic n-node subtournament. This is the directed graph analog of what has been called R. The smallest number Z such that any two coloring of the edges of a complete undirected graph with Z nodes contains a monochromatic complete graph on n nodes. We have R equals 0, R equals 1, R equals 2, R equals 4, R equals 8, R equals 14, R equals 28, 32, R 55, and R is again a problem, according to Ordos, that one does not want powerful aliens to pose.